Welcome to Control Core Tech, where we bring engineering to life through stunning animations and easy-to-understand explanations. Whether you're a student, a technician, an engineer, or simply curious about technology, you're in the right place. Every second, billions of electric motors are silently at work. They pump clean water into our homes, cool hospitals, move elevators, power factories, and drive trains. Yet most people never stop to ask one simple question. How does a heavy metal rotor begin spinning without anyone touching it? The answer lies in an invisible force that changed the modern world forever. More than 70% of the electricity used by industry is consumed by electric motors, and the AC induction motor is the most common of them all. It has no brushes, no permanent magnets, and no direct electrical connection to its spinning rotor. Even so, it converts electrical energy into smooth, reliable mechanical motion with remarkable efficiency. But how is that possible? Before we discover the invisible force that makes this machine rotate, let's explore its main parts. On the outside is the strong metal housing that protects everything inside. A cooling fan removes heat during operation, while bearings allow the shaft to rotate smoothly with minimal friction. Attached to the frame is the nameplate, which tells us important information such as voltage, frequency, power, speed, and current. Let's remove the outer housing and look inside. The motor has two main parts. The stationary outer part is called the stator, and the rotating inner part is called the rotor. A very small air gap separates them, but they never touch. The stator's job is to create a magnetic field, while the rotor's job is to respond to that field and produce mechanical rotation. Everything that happens next begins with these two components. Wrapped inside the stator are copper windings. When three-phase AC electricity flows through these coils, each phase reaches its peak at a different moment. Instead of producing one fixed magnetic field, the three phases work together to create a magnetic field that continuously rotates around the inside of the motor. This spinning magnetic field is completely invisible, yet it is the true driving force behind the entire machine. Imagine three people standing around a circle. Instead of pushing at the same time, they push one after another in perfect sequence. The force appears to move smoothly around the circle. Three-phase electricity behaves in exactly the same way. Each electrical phase reaches maximum strength at a different time, creating a magnetic field that seems to spin continuously around the stator. At first, the rotor is standing still. As the rotating magnetic field sweeps past its aluminum bars, it cuts through the conductor. According to the principle of electromagnetic induction, this changing magnetic field induces an electric current inside the rotor without any direct electrical connection. Those induced currents create their own magnetic field, and the interaction between the two magnetic fields produces torque, causing the rotor to begin spinning. Now here's something surprising. Even though the rotor keeps accelerating, it never actually catches the rotating magnetic field. If it did, the magnetic field would no longer move past the rotor bars. Without that relative motion, no current would be induced in the rotor. And without induced current, there would be no magnetic force, no torque, and the motor would stop producing useful power. This small difference in speed is called slip, and it is the secret that keeps an induction motor running. The rotating magnetic field always travels a little faster than the rotor. That speed difference continuously induces current in the rotor, allowing it to generate torque. Under light loads, slip is very small. As the load increases, the rotor slows slightly, slip increases, and the motor produces more torque to meet the demand. Once the rotor reaches its normal operating speed, the motor continuously converts electrical energy into mechanical motion. The spinning shaft can now drive almost anything, from pumps that move water to compressors that produce air pressure, conveyor belts that transport products, and giant industrial machines that keep factories running. All of this happens because of an invisible magnetic field working silently inside the motor. AC induction motors are everywhere. They circulate clean water through pumping stations, power ventilation systems in hospitals, move elevators in skyscrapers, drive conveyor belts in factories, cool buildings through HVAC systems, operate compressors, and automate production with industrial robots. Their simple construction, high reliability, and low maintenance have made them one of the most important inventions in modern engineering. Let's bring everything together. Three-phase AC electricity flows into the stator windings. creating a rotating magnetic field. That moving field passes through the rotor bars and induces an electric current. The induced current creates its own magnetic field, which interacts with the stator's field to produce torque. The rotor spins, driving the output shaft and powering machines around us. The rotor always stays slightly behind the rotating field, allowing induction to continue. The next time you see a water pump, an elevator, a factory conveyor, or even the fan cooling your room, remember that an invisible rotating magnetic field is doing the hard work. No gears are needed to start the rotor, and no brushes transfer power to it. Instead, electromagnetic induction quietly converts electricity into motion, making the AC induction motor one of the greatest engineering achievements in history. Now that you understand how an AC induction motor works, you have seen how electromagnetic principles transform electrical energy into motion. If you enjoyed this deep dive into engineering, subscribe to Control Core Tech and let us know in the comments which machine or technology you'd like us to explain next. Thank you for watching and for being part of the Control Core Tech community. See you in the next engineering journey.